In this section, we're going to be exploring implicit differentiation. As the name suggests, this is taking the derivative, but implicitly. We need to decide what the difference between implicit and explicit is. To do that, I've highlighted a couple of equations and written another one down for you. When we talk about an explicit formula, it means that it has been solved for the variable y, or for function notation f of x. In that case, the f of x is replacing y. Y is isolated by itself on one side with a 1 coefficient. On the other side is an expression in terms of only the dependent variable, usually x, but sometimes t. The equation highlighted in yellow, e to the x times the quantity x cubed minus 2, is an explicit equation in x because it's solved for f of x. What would an implicit equation be? The one over here in blue is an implicit equation because we have y minus sine y equal to 3x squared. Y is both outside of the trig function as the first term and inside the trig function sine. In fact, there is no way to solve that equation for y by itself. You cannot write that curve in the form y equals. If you took the arc sine to try to get at the y inside sine, you will vary the outside y inside of the arc sine. It's just not possible. Are there times when you can solve for it explicitly? Of course. The equation down here, y plus 32x equal to x squared minus the square root of x, can definitely be solved for y explicitly. There are times, however, where it might be easier to take the derivative implicitly and then to find the slope of the tangent line from there. When using the implicit formula, the derivative often has the variable y and x in it. That means that we'll have to know not just the x coordinate of the point where we want the derivative, but also the y. This is a slightly more difficult topic than what we have discussed in the past. It will come up more than once this semester, but it will come up more often as your mathematical subjects get more complicated in calculus 2, 3 differential equations. It doesn't come up all the time, but it comes up often enough that we need to learn it. We'll be exploring this in both this section and the next section when we look at an application of it in the logarithm. We'll be looking at logarithmic differentiation in the next section, which is really taking the natural log of both sides and then doing implicit differentiation. So the technique in this particular section will get used extensively in the next section. Let me share my screen with you and we'll get going. You'll see down here that we have relatively few learning objectives for this particular section. Namely, find the derivative of a complicated function by using implicit differentiation. Now, it could be that it cannot be solved for y explicitly. So implicit differentiation is our only way to find the derivative. Or it could be something where maybe it could be solved for y directly, but it would either greatly complicate the expression or make the derivative more difficult to find, in which case maybe implicit differentiation is better. Then, of course, we'll use this to find the equation of the tangent line after using implicit differentiation to find the derivative, the slope of the tangent line. Let's start by reading the definitions of both explicit and implicit, and we'll talk about how these apply to the derivatives. Explicit is something fully revealed or expressed without vagueness, implication, or ambiguity. leaving no question as to its meaning or intent, fully developed or formulated. In mathematics, it's an expression containing only the independent variable. In other words, it's solved for y, the dependent variable. Implicit means capable of being understood from something else, though unexpressed, implied, involved in the nature or essence of something, though not revealed, expressed, or developed. And the mathematical function is defined by an expression in which the dependent variable y and the one or more independent variables, for us x, are not separated on opposite sides of an equation. We've already looked at a couple of examples. What we're going to do now is we're going to talk about how we actually do implicit differentiation. What's the problem-solving process to find the derivative of an equation like the example in the introduction? Y minus sine of y equals, I can't remember what it was, x squared? All right, let's now take a look at some other examples so that we can fully understand what the difference is between explicit and implicit. This equation right here, x minus y squared equal to 0, is written in implicit form because it does not say y equals. Now, if we solved it for y, we would have to move each term to the opposite side of the equation and then take plus or minus the square root. However, it would be easier to take the derivative in the implicit form because of the radical in the explicit form and the plus or minus. In fact, as we'll discover with the equations to ellipses, which aren't functions, but are curves that do have derivatives, solving for it by taking plus or minus the square root makes the derivative in some cases impossible to find. And we'll see why in one of our examples. Now, this next one is not easy to make explicit. It's not only difficult, but it requires a restriction on the variable that the original problem does not carry, namely that y cannot equal 1. Let's look at this example. In this equation, x plus y cubed minus xy equal 1, we have y showing up in two different terms. Our x variables are not separated from y, so we know that this is in implicit form. In order to solve for y explicitly, we're going to first write y cubed minus 1, and on the opposite side equal xy minus x. This is not a technique that's always going to work. It only works here because y cubed minus 1 can be factored, and because the opposite side of the equation can be factored to produce an identical factor. Now, the problem is, when you divide by that, you're saying that y will not be 1 because that would cause division by 0. So in fact, you're implying that you have omitted 1 from the domain. It may or may not have been allowed by the original equation. Now, when we look at the reduced equation, we have y squared plus y plus 1 equals x. It's quadratic in y, but this x term isn't a y term. That makes it part of the constant term. So the coefficient of the quadratic term is 1, the coefficient of the linear term is 1, and the constant is everything else, including the variable x. It becomes 1 minus x. We apply the quadratic formula, simplify, and we get finally an explicit form to the original equation. Y equal negative 1/2 plus or minus the square root of 4x minus 3, all divided by 2. Yes, we could take the derivative in this explicit form, but in fact, it would be easier to take the derivative of the first line in its implicit form. This next equation that we see here, it would be impossible to solve for y, much like the example in the introduction. We have e to the xy power equal to 2y. The y is both in the power for the exponential and on the opposite side of the equal sign as the 2y term. If you take the natural log to get at the power xy, that will put the 2y inside a natural log where you can no longer get your hands on the y. It's not possible to write this equation in the y equals explicit form. The technique of implicit differentiation is going to let us find the derivative, whether it's solved explicitly for the variable y or not. It will give us an expression for the derivative without having to have that y equals. Don't forget, though, that y is still the dependent variable, and it does depend on x. Since we're taking the derivative with respect to x, this is going to invoke the chain rule. Y is not x, but it's a function of x. When you take the derivative of y, you get dy dx. This is the chain rule. Let's go over our problem-solving strategy for implicit differentiation, and then we'll work a lot of examples to make sure you understand the process. First, we take the derivative with respect to the independent variable, usually x, but sometimes t, of both sides of the equation. When we encounter a y, the derivative of y will be dy dx, because y is a function of x. So if I take the derivative with respect to x of sine x, I just get cosine x. The derivative with respect to x of sine of y invokes the chain rule. The outside function is sine, the inside function is y. So I get derivative of the outside, cosine, with y still inside it, times the derivative of y, dy dx. This is the chain rule. In the next step, we're going to rewrite the equation so that any term, something plus or minus something else, on either side of the equation, all the terms that contain dy dx are on the left side of the equation, and all the other terms that do not have dy dx as a factor are moved to the right side of the equation. We're trying to find dy dx. That's our whole goal, is to solve for the derivative of y with respect to x. So our third step is to factor out the dy dx from the left side of the equation as a common factor. It may not be the greatest common factor, but I don't want the greatest common factor. I only want dy dx. So I only bother to factor out dy dx. In the fourth step, I'm going to solve for the derivative dy dx by dividing both sides of the equation by whatever its factor next to it is. This may leave a y variable in the expression of dy dx. This is common when we're using implicit differentiation. If I know the explicit formula for y, I can replace the y with that formula once I've applied implicit differentiation. If I don't know how to solve for y explicitly, I'll simply leave the y in the expression for dy dx. Let's now apply this rule to the simple one we had at the beginning, x minus y squared equals 0. It's an implicit form because it's not y equals. We know we could put it into explicit form by moving the y squared to the right side and taking plus or minus the square root of x. We're going to think of the y squared with the square as the outside function and y as the inside function. We're going to take the derivative of both sides with respect to x. When we take the derivative of both sides with respect to x, the derivative of x is just 1. But the y and the differential dx do not match. Y is itself a function of x. So I apply the power rule on the outside, 2y to the first, and multiply by the derivative of the inside, dy dx. The derivative of the constant 0 is, of course, going to give me 0. This is step 1. Take the derivative of both sides. Step 2, we want to isolate any term with dy dx on the left, and all other terms without dy dx go to the right. I isolated and got 2y dy dx equal 1. The next thing we want to do is factor the dy dx out as a common factor from the left side of the equation. There may be more that could be taken out, but I only need to take out dy dx. Factor it off of the 2y, and in the next step, I'm going to divide by the associated factor next to dy dx, the 2y. Notice in my derivative here, I have y represented on the right-hand side. This is not an explicit formula for the derivative, but implicit where the y is still involved. Now, this is common for implicit differentiation. If I had taken the derivative after solving for y explicitly, I would still have this plus or minus inside of my derivative. The derivative of square root x is 1 over 2 the square root of x, since the derivative of x is 1. That would still give me a plus or minus. In the implicit one, if I knew the value of y, I would know what the actual slope was at that point. I wouldn't have a plus or minus to worry about. That's one of the advantages of the implicit differentiation process. But the disadvantage is I have to know the y value at the point, not just the x value. With explicit differentiation, all I need to know is the x value where I'm taking the derivative. For implicit, we often need to know both x and y. Let's now take a look at finding the slope of the tangent line at the point 4, 2 on the example we just worked. Using the implicit derivative formula, 1 over 2y, I know the y value at the point is 2, so I get slope of 1/4. There's no ambiguity and no plus or minus. If I had solved for y explicitly and found the derivative, I would have dy dx equals 1 over plus or minus 2 the square root of x. I would then have to figure out which arm of the sideways parabola the point is on to decide whether the slope was positive or negative before I could complete the problem. Let's now look at example 1. In example 1, we have the equation 4x to the 5th plus tangent of y equal y squared plus 5x. This is an example of one that cannot be solved explicitly for y. This is the only technique to find the derivative of y with respect to x, because the y is both outside and inside a trig function. Remember our steps when we do this. Step number 1 is to take the derivative of both sides. This means that I get the derivative with respect to x of 4x to the 5th plus tangent of y and set it equal to the derivative with respect to x of y squared plus 5x. As long as I apply the same operation to both sides, it should still be balanced. This is going to give me 20x to the fourth plus the derivative of tangent is secant squared, freeze the inside as y, and then multiply by the derivative of y, which is dy dx. On the right side, the outside function is the square, the inside function is y. So I get 2y to the first times the derivative of y, dy dx. The derivative of 5x with respect to x is just 5. This is the first step. Take the derivative with respect to x or whatever the independent variable is on both sides. Next, we want to isolate dy dx terms. If we gather our dy dx terms on the left side, I would have secant squared of y dy dx minus 2y dy dx equal to the two terms that don't have dy dx, 5 minus 20x to the fourth. The next step is to factor out just the dy dx. This leads to dy dx times the quantity secant squared of y minus 2y equal to 5 minus 20x to the fourth. Finally, we divide by the factor multiplied by dy dx to get an implicit expression for the derivative of y with respect to x. If I want to use this formula to find the slope of the tangent line, I will have to know both the x-coordinate and the y-coordinate at that point. I need more information because it was an implicit equation. Let's now take a look at another example, number 2. We'll work a couple of these together and then I'll start pausing to let you work some of them out on your own. Our first step is to take the derivative of both sides with respect to x. This gives me the derivative with respect to x of xy minus cosine of xy equal to the derivative with respect to x of 1, which is going to be 0. The xy's are going to give me the product rule. So I get 1 times y for f prime g for the first one. And somehow my minus got too close to that term. Plus, now I do the derivative of y, which is dy dx, times x, g prime f. Oops, lost my d. Then I need to take the derivative of negative cosine of xy. The outside function is cosine, and the derivative of cosine is negative sine. So the derivative of negative cosine is positive sine. So I'll get sine, freeze the inside as xy, now multiply by the derivative of xy, which we've already done once, so we can just simply rewrite the result here. And this is equal to 0. In order to continue this problem, we need to simplify it. This will give me y plus x dy dx plus y sine of xy plus x dy dx sine of xy, still equal to 0. My next step in the problem-solving process for implicit differentiation is to then gather the dy dx terms. When I gather the dy dx terms, I get x dy dx plus x dy dx sine of xy equal to negative y minus y sine of xy. In my next step, I factor out the dy dx and only dy dx. It is true that I have a common factor of x as well on the left side, but I really only want the dy dx. So that's all I take out. And this leaves x plus x sine of xy in parentheses. And in my next step, I'll divide by that. The right side is unchanged. In the final step, we want to solve for dy dx by dividing by its factor. Again, this is an implicit formula for the derivative, so I will have to know both the x and the y coordinate at the point in order to find the derivative, the slope of the tangent line at that point. Let's look at example 3. In example 3, we see that we have y outside of the trig function in 2 places and y inside the trig function. This will make it impossible to isolate y on one side of the equation. Implicit differentiation is the only way we can go. I have a product rule twice on the left. Y times sine of xy. Y and sine are product rule. Sine is also chain rule. Sine on the outside, xy on the inside. Xy is also the product rule. On the right, y squared is still chain rule. The outside is the square and the inside is y. It's not an x, so the derivative with respect to x is dy dx. Go ahead and pause the video, work it out, then turn the video back on and we'll compare. Let's compare our results. First, we take the derivative of both sides. This will invoke the product rule first on the left, where f is the variable y and g is the sine of xy. This will give me f prime dy dx times g sine of xy plus the derivative of g, which will be both chain rule and product rule. I get the derivative of sine as cosine, freeze the xy, times chain rule, the derivative of the inside, which is the product. Again, I have an f prime g plus g prime f, giving me y plus x dy dx. Then I have to multiply this by, g prime, this should be f. I think I got a little carried away with my g's. There's my f. And then all of that multiplied by y. On the right, this is chain rule. The power 2 is the outside function, y is the inside, 2y dy dx, and the derivative of the constant 2 is 0. Next, we're going to simplify by distributing across these parentheses. It's probably easier, frankly, to take this single factor y here at the back and write it in front of the cosine so you don't lose track of it. Then you can distribute across what's inside the parentheses next to it. We get dy dx sine of xy plus y squared cosine of xy plus xy dy dx cosine of xy equal to the right side 2y dy dx. Then we gather our dy dx terms on the left and we move the single term that does not have dy dx to the right. Finally, we want to factor out the dy dx and then divide by its coefficient. And this will give you the derivative in implicit form, negative y squared cosine of xy divided by sine of xy plus xy cosine of xy minus 2y. Again, to actually find the slope of the tangent line, we would need both coordinates, not just the x coordinate. Go ahead and pause the video to work out example 4 as well. Let's compare our work. This one's a bit more straightforward because it doesn't have as many product rules and chain rules. It does have 2 product rules, however, but they're within polynomial expressions. So I take the derivative of both sides, I apply the product rule to x cubed y, giving me 3x squared y plus dy dx x cubed. And I apply the product rule to xy cubed, getting y cubed plus 3y squared dy dx times the x that was at the beginning. The derivative of -8 is a 0. Next, we gather our dy dx terms on the left and move the 2 terms that do not have dy dx to the right. And we factor the dy dx out, and finally we divide by its coefficient. This gives negative 3x squared y minus y cubed, all divided by the quantity x cubed plus 3xy squared. I do have a common factor of y in the numerator, but it is not common in the denominator because it's not in the x cubed, which means unless I can factor it out and change the numerator and denominator into things with parentheses around everything, and I am not allowed to cancel. Let's now turn our attention to problem number 5, where we're going to find the equation of the tangent line to the graph of the given function at the indicated point. Then we'll use Desmos to look at both the function, the point, and the tangent line. I'm going to move some blank lines down so I have more space. First, to find the equation of the tangent line, I've got to have the derivative. But this is an implicit equation of y in terms of x. Y is both inside and outside a trig function, so it is impossible to solve this for y. I'm going to have to do implicit differentiation. Go ahead and pause the video and compute the formula for the derivative. Then turn the video back on and we'll finish the problem together. First, we take the derivative of both sides. On the first term, we have to apply the product rule and also the chain rule for the y squared part. Product rule gives us y squared plus 2y dy dx. Remember, y is an inside function times x, the original f. The second term is chain rule only. Outside is sine, the inside is pi y. Remember, pi is just a constant. So I get cosine of pi y, brings the inside, times the derivative of pi y, which is pi dy dx. The derivative of the third term, negative 2x squared, is negative 4x. And the derivative of the constant 10 on the right is 0. The next thing we're going to do is gather together our dy dx terms. When we gather our dy dx terms, we'll next be able to factor them out and solve for dy dx. When we factor out dy dx and divide by its coefficient, we end up with 4x minus y squared, all divided by 2xy plus pi cosine of pi y. In order to find the slope of the tangent line at a point, I have to have both the x and y coordinate because I have both x and y in the derivative formula. I rewrote the equation and the point down here so we would be sure that we knew what we were looking for. I want to find the derivative of y with respect to x, specifically at the point 2, 3. This means evaluate dy dx at the point 2, 3. So I'll substitute 2 in place of x and 3 in place of y, everywhere they occur in the derivative formula. Starting in the numerator, 4 times 2 is 8, 3 squared is 9, and 8 minus 9 would give me a negative 1. In the denominator, 2 times 2 times 3 will give me 12. And then I have pi times the cosine of 3 pi. 3 pi, of course, is pi past 2 pi, and 2 pi is back around at 0. So the cosine of 3 pi is the cosine of pi, which is a negative 1, giving me 12 minus pi in the denominator. So negative 1 divided by 12 minus pi is the slope of the tangent line at the point 2, 3 on the graph of this function. If we want to write the equation of the tangent line, then we would have to write y minus 3, the y coordinate of the point, equal negative 1 over 12 minus pi, the slope of the tangent line, times quantity x minus 2, the x coordinate of the point. Let's now take a look at the graph and see what it looks like. Oops, wrong one. There we go. It's kind of an interesting graph. Because of the sign, there's a little bit of an oscillation coming up here that you may be able to see if you zoom in close enough. And now we can see the point 2, 3, and we have the tangent line graphed, and indeed it is tangent at that point. All right. Let's now move on to example number 6. In example 6, you want to find the equation of the line tangent to the hyperbola at the point 5, 3. When we're looking at this one, we have an implicit formula, x squared minus y squared equals 16. And we want the tangent line at the point 5, 3. You can verify that 5, 3 does rely on this curve. It is not, in fact, a function. I believe it opens left and right. So it's not a function, but it is a curve. Go ahead and pause the video, find the formula for the derivative and the slope of the tangent line, and turn it back on, and we'll compare our results and look at the graph. Again, you're first going to take the derivative of both sides. This leads to 2x minus 2y dy dx equals 0. Then we isolate the dy dx term on the left and move the 2x to the right. Factor the dy dx out and divide by 2y. Notice the 2 is a common factor, and without addition or subtraction in the numerator or denominator, I'm allowed to cancel it, so I get the formula x divided by y. The next thing that I want to do is evaluate this at the ordered pair 5, 3. When I substitute that in, I get the value of 5/3. So I'm able to write the equation of the tangent line, y minus 3 equals 5/3 times the quantity x minus 5. Let's take a look at the graph so that you can verify that it meets your conclusion. And indeed it does. You can see the hyperbola here in black, definitely not a function, but it is a curve. And you can see that at 5,3, you have graphed the actual tangent line. Let's try to solve for y explicitly and take the derivative from that formula. In this case, I will move the 16 and the y squared to get y squared equals x squared minus 16. Then I have to take plus or minus the square root, giving me x squared minus 16 under the radical. Now, in order to find dy dx, I take the derivative. The derivative of the square root is 1 over 2 the square root, in our case, with a plus or minus. The derivative of a radical is 1 over 2 the square root multiplied by the chain rule derivative of the inside, which would be 2x. This would give me a final formula of x divided by plus or minus the square root of x squared minus 16. The problem is the plus or minus isn't indicating which one I have. There are two located at different points. The problem is here with the x. Is it a 5 or is it a negative 5? Right? And also with the y. When I look at this, I'm going to get a different tangent line depending upon the point. I have to know whether it's plus or minus, which I would only know by going to the graph and looking at the function that you see here. You can see at 5/3, it should be a positive slope, or 5/3, it should be a positive slope of 5/3. What do you suppose the slope of the tangent line is at negative 5/3? You're correct. At negative 5/3, it would be the opposite of 5/3, negative 5/3. There's an ambiguity then in this particular problem when solving for it explicitly that we do not have when we solve for it implicitly. Let's now take a look at example 7. In example 7, we're given the implicit equation tangent of xy plus equal x plus y at the origin. And we want to find both the curve and the tangent line. Go ahead, work this out, and then come back and we'll compare our answers. Again, we take the derivative of both sides using chain rule and product rule on the tangent of xy. Derivative of tangent is secant squared, freeze the inside at xy, then multiply by the derivative of the inside using the product rule, y plus x dy dx. On the right side, take the derivative of x plus y to get 1 plus dy dx. Then we need to distribute across this addition on the right or left side. Then, after we've done that, we're going to gather all of our dy dx terms on the left and our non-dy dx terms on the right. When we're done with that, we'll factor out the dy dx and then divide by its coefficient, giving us a formula for the derivative of y with respect to x. Quantity 1 minus y secant squared of xy divided by the quantity x secant squared of xy minus 1. We wanted to find the slope of the tangent line at the origin, so we replace both x and y with 0. Now, secant of 0, of course, turns out to be the reciprocal of cosine of 0. And the cosine of 0 is 1, and 1 divided by 1 is still 1. However, it's multiplied by a 0 in both cases, so those terms 0 out. And we're left with 1 divided by negative 1, which gives us a slope of -1. Using point slope and simplifying, we get the tangent line to be y equals -x. Let's now look over here and see if we can find this particular one. You can see that this is a very, very complicated graph. Clearly not a function. And in fact, Desmos is having trouble drawing it. Probably these should be connected instead of dotted, but it's changing so rapidly, it's not able to figure it out. But we can see that at the origin, the slope of the tangent line is -1. We now want to turn our attention to example 8. Example 8 is an application problem. In this, we have a circular cone, which of course looks like a witch's hat, or an ice cream cone. And we want to find the volume by using the formula 1/3 pi r squared times the height. In this case, x is the radius and the height is given by y. So our equation is 1/3 pi x squared times y. The volume of the cone is to be a constant. We want to find the rate of change of the height, y, with respect to the change in the radius, x, when x is 4 and y is 16. In other words, assuming that v is a constant number whose derivative will be 0, do implicit differentiation and come up with a formula for dy dx. You could, of course, also try to solve for it explicitly, and then you could do it that way. Then find the slope of the tangent line, and we'll compare. Again, we take the derivative of both sides first. The derivative of the constant number v is 0. And on the right, I chose to factor out 1/3 pi since it was just a constant coefficient. That gave me the product rule on x squared y, 2xy plus x squared dy dx. The next thing I did was to distribute back the pi and the 1/3. Then I isolated the term with the dy dx, and then I factored it out and divided by the coefficient. This was able to reduce both the pi, the 1/3, and one of the x terms from, or x factors from the denominator. This led to a formula of -2y divided by x. When x is 4 and y is 16, I get a rate of change of -8, meaning that the height is decreasing 8 units for every 1 unit of increase in the radius. Let's now take a look at example number 9. In example 9, we have an exponential. This is actually one section early, but I hate to miss the opportunity to do implicit differentiation with an exponential. So I've given you the formula for the derivative of the exponential here. The derivative of e to the u with respect to x is going to be e to the u du dx. That's the one with the chain rule built into it. Let's now go ahead and apply the derivative to both sides of this implicit equation. Notice there's no way to solve for this explicitly. Y is both in the power on the exponential and not in the power on the exponential. When I take the derivative with respect to x of both sides, the derivative of e to the xy is e to the xy times the derivative of xy, which is 1 times y plus x dy dx. On the right side, when I take the derivative of 2y, I have to invoke chain rule since y is an inside function. This gives me 2 dy dx. Now I need to simplify so that I can get everything out in the open. This gives me y e to the xy plus x e to the xy dy dx equal to dy dx. Next, we gather our dy dx terms on one side of the equation. This is going to give me x e to the xy dy dx minus 2 dy dx equal to negative y e to the xy. In the gather term, we're only adding and subtracting things from one side of the equation to the other. Then we factor out the dy dx, and we solve by dividing by the coefficient. This gives me dy dx the formula for dy dx becomes negative y e to the xy power divided by x e to the xy power minus 2. It is tempting to want to cancel the e to the xy's. The one in the denominator has 2 subtracted from it, which means that it's part of a term. Unless it's common to every term in the denominator and you can factor it out, then you cannot cancel it. Let's take a look at our last example, number 10. In example number 10, you're asked to find the second derivative of y with respect to x both times. The equation is written implicitly because we have the y both inside and outside of the trig function. Go ahead and compute the first derivative with respect to x. And then if you want, you can unpause the video and we'll explore the second derivative together. This particular problem is not too bad as far as finding the first derivative, but as we'll see, the second derivative is more complicated. Take the derivative of both sides, and you get cosine y dy dx, and then applying the product rule, y plus x dy dx, and the derivative of 4 is 0. Gather your dy dx terms, factor out the dy dx, and divide by the coefficient to get negative y divided by the quantity cosine y plus x. Now we want to find the second derivative. It is explicitly solved for dy dx, but it's an implicit formula in that it has both y and x in it. When we take the derivative of this again with respect to x, every time we encounter y, we will again have to invoke chain rule. Let's go ahead and do that now. And hopefully I have left enough room. To find the second derivative, we're going to take the derivative of the first derivative. That means that we have a quotient, or you could put the first denominator in parentheses and raise it to the -1 power. In other words, you could write this as negative y to the cosine of y plus x to the -1 power, and then apply the product rule. Which would you rather do? I'm guessing the product rule with chain rule, so we'll try that one. This is going to give me the negative y as f, and the entire thing raised to the -1 power as g. When I apply the formula, the derivative of negative y is negative dy dx. That gives me f prime, then I multiply by g. cosine y plus x raised to the negative 1 power. Then I'm going to have to do g prime f. I applied the power rule on the outside to get negative 1 times cosine y plus x, now raised to the negative 2. Now I multiply by the derivative of the inside. The derivative of the first term, cosine y, will give me negative sine y dy dx. The second term will give me a derivative of 1. Now what I want to do is rewrite this in such a way that it's a little bit easier to evaluate by moving the expressions with negative exponents back into the denominator. We do have the opportunity to get a common denominator, but I'm not sure it would be of great use to us, so I may or may not do it. It depends on how complicated things get. The next step is actually straightforward once you know that's what you're supposed to do. I need to replace these two y dx's with the expression I found for the first derivative. So now I can rewrite the second derivative as, since I have a negative, it makes it double negative, which makes it y over cosine y plus x, all divided by cosine y plus x. Now, this is a complex fraction, and the numerator of the numerator is y, and this cosine y plus x is denominator of the numerator. This cosine y plus x is numerator of the denominator. So the two cosine y plus x's will end up together in the denominator. For the second part, I could distribute the negative, which would reverse the signs inside parentheses. That probably would be a relatively good use of some algebra, except that when I look at the formula for dy dx, I see that it has a negative attached. And I know it's going to be multiplied by the term that has the negative. So I'm going to leave the negative 1 by moving it between the two fractions. And I'm going to then multiply the negative sine of y times the expression for the first derivative. Then we add 1. All of this is divided by the cosine of y plus x to the second. The double negative gives me a positive, but I still have a complex fraction. I'm going to have y sine of y divided by cosine y plus x. To get a common denominator with the first one, I could multiply by cosine y plus x over itself. But since it's complex, what I probably want to do is multiply by the least common denominator of the little denominators. And that, in fact, turns out to be just the cosine of y plus x. When I multiply by cosine y plus x over 1 over cosine y plus x over 1, I can then rewrite it in a better form. Unfortunately, I think I'm out of room, but let me see what I can do here. The first term stays the same, y over cosine y plus x quantity squared. And the second term, the cosine y plus x, cancels with this first factor and gives me y sine of y. And then I get this multiplied by 1. So for the next one, I would have y sine y plus cosine x, y plus x, all divided by, and now I have 3 cosine y plus x to the third in the denominator. Kind of ran out of room there. All right. I hope this is making sense to you and that you can understand how to do these particular types of problems. In our next video, we'll be taking a look at exponential and logarithmic derivatives. We have gone ahead and covered exponential, but we need to talk about the derivative of the logarithmic function, the inverse function to exponentials. Then we'll learn a technique called logarithmic differentiation, which can help us to expand certain very complicated expressions so that we can take the derivative more easily. The next section will be our last section in our initial study of the derivative. But chapter 4 deals with applications of the derivative. I hope to see you soon.